Hi, I'm Rob Sherwood, CTO at Big Switch Networks, and today I'm going to talk about our Big Cloud Fabric product. So our Big Cloud Fabric product implements standard data center switching functionality with a scale-out leaf-spine fabric. So we've got a centralized controller that manages a collection of 1U leaf and spine switches as if they were one big switch. The goal is to not ever have to get you to log into these switches to manage them. And we've got all sorts of open APIs to our controller, and with those APIs, we've extended support for OpenStack, which I'll talk about. We've got some fun new support with VMware that we've got a full demo about. And as I was mentioning in the last section, all of this gets managed from a single point of control. So you could always build a network out of leaf and spine switches. But then if you wanted to trunk a VLAN from one place to another, you'd have to log into each box along the way. That's annoying, specifically when you screw it up and you don't know where you screwed it up. And you don't realize that you screwed it up because it was on a backup path. And you only figure it out once the backup path fails over. And maybe if it's browning out, it only fails over sometimes. And too much about past lives with me. But with a controller, you don't have that problem anymore. The controller automatically programs everything in a consistent way.
Hyper-V coming, or?
There are thoughts about that. Honestly, we haven't run into it that often. But I mean, it's very.
We support Hyper-V. It's that the integration piece is not there.
Yeah.
We have integrated into OpenStack and VMware environments today.
KVM.
Much better answer.
KVM. OpenStack is KVM,
yeah.
Right?
So, and this is new as of yesterday. So, before yesterday, we only supported control of the physical switches. Now, and this comes back to the nuance to Prashant's answer and why it was better than mine, we can also control virtual switches in a KVM environment. So that is not only are we controlling the physical leaf-spine fabric, we're also controlling the virtual switch that actually sits on the server.
Can you do it at L2 and L3 with OpenStack with hardware?
Say again?
Can you do it at L2 and L3 at
Yes.
hardware VTEPs with OpenStack?
Yeah. And that's the thing, like jumping specifically to OpenStack, and I do have a whole bunch of slides about it. Everyone we talk to is having problems scaling out the L3 agent. And with our solution, not only do you get software distributed routing, we actually get hardware distributed routing. So it works both for your VMs as well as your bare metal and appliances. And I've got a whole sequence of slides about that.
So ECMP and
Sorry?
all ECMP.
Yep.
And all the likes across. Okay.
So actually, I didn't say, maybe importantly, actually let me go, I'll use this slide for it just while we're on it. All links here are active-active. Okay. And the connection between any 2 points, whether it's L2 or L3, is actually a matter of policy, not topology. So basically you can program the L2, L3 boundaries arbitrarily through this mesh. Kind of the quip that I like is every switch is a router and every router is a switch.
And from an end user perspective, that means you can have IP anywhere. So if you want to do vMotion on a very large fabric, you can get there. Or if you want to treat it as a huge L3 router, you get that as well. So it's purely based on policy, not based on anything else.
Did you say you were going to talk about the OpenStack integration / virtual layer later? You have slides dedicated to that? Okay, cool.
So one big use case is deploying with OpenStack. That is where we own both the physical and the virtual layer. And I'll talk about that in some detail. Another completely different use case is deploying with VMware, where we don't own the virtual switch, we only own the physical fabric. But that's actually still really valuable. It turns out there are non-VM related networking problems in the world. And a completely different use case is there are people in the world who don't use VMs. I know that the popular press might forget about this, but there's lots of big data workloads, there's lots of legacy database workloads. And so just having a physical network is pretty useful sometimes. So these are kind of the three high-level use cases for how we use Big Cloud Fabric. No questions so far. And it's a standard data center switch. You can use it for lots of use cases. I will say that our customers tend to focus around infrastructure as a service, kind of private cloud deployments, big data, high performance computing, virtual desktop infrastructure. Those seem to be kind of the big things so far. I don't know if that tracks with what you guys are seeing, but that's where we're seeing the most growth. What this looks like in practice is you have racks of servers. The recommended deployment is 2 switches at the top of each rack for redundancy. We then collect all the spine switches in one rack. We put 2 physical controllers in that rack, so our controllers actually deploy as an appliance. And if you've got OpenStack, you can hook that in here. If you're using our vSwitch, our Switchlight V switch, that pops into the servers here. This is all optional. Is it clear what this looks like in practice? I know last time we actually took you guys to the data center that we have downstairs, so you can actually see this. I don't know if there's going to be time for that this time.
Makes sense. Yeah.
So, question. So, do both controllers have to be in the same chassis?
They don't have to be in the same chassis. It's you'd probably want them in at least different power planes.
Right.
Although, as Prashant said, because of the resiliency metrics that we've built in, so it's an active standby configuration. So if the active controller goes down, it's actually 0 packet loss for the standby to take over. If both go down, which, by the way, in a chassis-based switch, if you've lost both supervisor cards, the thing was a brick, right? It's completely useless. But if both controllers go down, we actually keep packet forwarding. So I think where you're going with your question, it's actually less of a concern to have both controllers in the same chassis, but it doesn't have to be that way. Frankly, it was just easier to draw.
How do you handle? How do you handle Mac moves? So if you have both controllers die, obviously that's a very bad scenario.
Yeah.
But if you have a Mac move, right? Let's say a vMotion across from one rack to another. How do you?
And that's
handle that
that's an important caveat too. When both controllers die, there are sets of things that stop working. So you can't obviously update the policy. There are certain error conditions that we can no longer handle because the controller has to get involved. And to your point, we actually do Mac learning through the controller, and so you actually can handle either Mac moves or new machines. But just don't kill both your controllers at the same time, and then all of that works.
Yeah, I wanted to go back to the earlier question. So we think of this as single soup in a redundant chassis, which is a normal deployment scenario. So that's so you get redundancy. So think of this as a pair of chassis or redundant, chassis pair.
Is there plans to expand to more than 2 controllers?
It's possible. The code's even written that way. We don't support that currently. It actually hasn't been real clear for the need. So going from active standby to active standby. I mean, we're open to it. We just haven't had the customer demand yet. We are absolutely not telling people to throw out their entire network. Hopefully this is obvious, but I've got this slide just to make it expressly clear. The idea is in a typical data center, you may have core routers, for your ingress egress. You may have stock legacy stuff. The idea is that we would slot in peering directly with the core routers. As you build out another row, as you build out another project, drop us in for that. So this is the picture of how we integrate with the rest of the world. Comparison of us versus a net frame, single point of control. Something you don't really think about, and probably take for granted. Your line cards are effectively stateless, meaning that you don't have to manage. There's an operating system on those. There's configuration that gets downloaded to them when you plug them in. We replicate that same thing with our zero-touch fabric. So when you take a switch from Dell or you take a switch from EdgeCore, and you get it from them, and you plug it into the network, and you turn it on, it actually will network boot off of our controller, and automatically download both its operating system as well as its config. The only thing that you have to do is on the controller side is actually give that switch a label by its MAC address and a role. Is this a leaf or a spine? And I'll talk more about that in a bit. There's a bunch of things that you kind of expect about a chassis switch, that we do all of those. Then there's a whole bunch of things that are actually problematic about chassis that we think that we actually solve. So when you buy a big chassis-based switch, you have to decide when you buy the switch, how big is your network going to be? And it's very rare that you get this just right. Most often, if you guess too small, that's bad because then you have to buy more. And so most people buy big and assume that they're going to try to grow into it. But maybe you do, maybe you don't. There's kind of stranded CapEx there. With our system, you can actually just scale out as you grow. Just, as you need more racks, you deploy a couple more switches, you plug that into the spine, you keep going. There's actually not even additional config update except for labeling it by the MAC address that I said.
But is there any limitation? How far can you scale out?
So the current limit is actually based on the Broadcom chips. So it's, and I should say this is per controller pair, so per pod, so you can have multiple pods pretty easily. But the idea is it's 32 leaves, which with redundant leaves is 16 racks. For most customers, 16, so people are either bifurcated. Either 16 racks is a huge amount of compute, or that's like one row out of your football field. And if that's one row out of your football field, just buy a couple more.
And once the spine changes to 64 by 40, this
Yeah.
will double. So it's really, the hardware is available today. That determines the size.
We do have tricks to make it bigger, but just practically speaking, there's actually this nasty design trade-off that people don't want to think about, which is how big is your splash zone, like how your blast radius. So 16 racks of compute, all controlled by even a very redundant control plane. I mean, you wouldn't hook. There's a limit to. So why don't they build chassis switches bigger than they do? Right. That people have already decided that there's a certain number of ports that make sense to have there. You can actually, in theory, build chassis-based switches. It's the same architecture. People have built, at least on the carrier side, like even bigger, like the CRS series and things like that. But there's all sorts of problems when we start going to multiple cabinets, and there's reasons why people don't do this. This is actually, at least in my opinion, the right bite-sized chunk to consume data center kit.
That's only today. I mean, tomorrow.
And this is only today.
And those numbers align to the biggest chassis too, right?
Exactly. For the same reasons. It's got the same chips inside.
But Rob, I mean, I could build a 5-layer cloth fabric instead if I wanted to.
Yeah.
If I needed more ports.
And so you can, not with this code as it's written. That said, even the, I won't flash back to the Facebook picture that they did with their Altoona data center. That's only 3 layers. So with each layer of cloths, you actually get exponential growth. So 2 layers gets you 16 fully redundant racks. 3 layers gets you a Facebook data center. No one has done a 4th layer as far as I know. Now, we absolutely have the technology to build a 3rd layer. The set of customers who are interested in that is actually fairly small. We're talking to them. We might do it, but it's more of a business question rather than a technology question.
So if I build out a series of different pods then with a maximum of 16 racks apiece, is there a way to federate all of those controllers together, or is there even a point in that?
Because we have open REST APIs to the controller, something that I'll spend some time talking about. So let me segue and come back to that question. The main interface to the controller, the first-class interface, is actually a REST interface. It's a programmable API. That said, we have a standard-looking, industry standard CLI that is a REST API client. It appreciates my jokes. There is a CLI, which is basically just a REST API client. You type all the same show running config commands that you know and love. It translates them into REST calls and sends them to the controller. I will demo fairly substantially the graphical user interface, which is also just a REST API client. And so this means that anything you can run at the CLI, anything you can run from the GUI, you can actually turn into an automated scripting something. Now, to Ethan's question, is there a way to manage lots of pods from a single point of control? We are looking at, effectively our own management system to do that, and that's something we're hoping to talk about, maybe a bit later.
Controller of controllers.
Yes. You said it, I'll repeat it, controller of controllers. It's a really interesting concept. It has a really bad acronym, so the marketing folks are still working on that. Oh, God. Particularly if you look at, never mind.
Controller.
So, reasons to buy our product. Let's stay on target. My fault. We actually have really interesting ways of programmably slicing and dicing the network. And I'll talk about this on the next slide. But the idea is, if you are a service provider, you actually have tenants, and having rich multi-tenancy features is really useful. If you're an enterprise, you actually still have need for this in terms of applications. And so a lot of people will talk about this as application-centric networking. They're really just fancy ways of slicing and dicing the network. I mentioned the zero-touch stuff. I'll talk about this in a little bit more detail. And one of my favorite features is the ability to do a hitless upgrade of the entire fabric. And I'll talk about how this works. But the short story is, because the data plane is redundant, because the control plane is redundant, and because the controllers have a perfect view of what everything is, it can actually selectively reboot and upgrade parts of the fabric without losing connectivity while the entire thing is running. And we can do this in under 15 minutes. So I'll talk about how that works. But that's something that I don't know that anybody else can do. So let me cover these 3 things in some detail, and we can cover questions on that. Make sense? You guys are with me? Okay.
Question actually on policy enforcement or configuration, pushing down to the devices. If you're adding a new segment, or let's say logical network segment, call it a VLAN if you will.
Yep.
When it's created, is it getting pushed at that instant to
at
all
that
nodes,
instance.
or is it only upon when, let's say, a server or VM needs that policy at that?
It is pushed at that instant. And so there's a bunch of good reasons for that, but that's how it happens.
Okay.
So Rob, just, and not necessarily a technical thing, but there's kind of an implication here, and I'm thinking about a lot of enterprises, that in order for the ONI stuff to work and for the controller, is that you really need an out-of-band management network for this to work, because you can't plug in and connect necessarily through the fabric you're trying to connect to, right? And I don't know around the table how many enterprises have bothered building an out-of-band management network, because I seem to find an awful lot who are still using SVIs and managing in-band. So it's certainly something that has to be thought about when deploying.
Absolutely agreed. Couple thoughts on it. One, yes, as this ships, it actually needs an out-of-band management network. But as pictured here, what makes this easier is that it doesn't have to be hooked up to anything else. So it can be actually a physically segregated out-of-band management network. So basically what happens is, out of these switches, there's a physically dedicated management port. It's on a hardware level, it's actually not even hooked up to the Broadcom chip. It looks much like an Ethernet card hanging off of the PC that drives the switch. That comes out of the switch and then hooks to, we've only got one pictured here, but to a dedicated management switch. This can be a Netgear or whatever floats your boat. And so inside a data center, so definitely in campus enterprise, I agree that a lot of people don't have like an out-of-band management network. At least it's been my experience that in data center that's much more common. And particularly if the requirement is only like hook things up to local inside the sets of racks, that seems to be less onerous. Now that said, this is what the product does today. Our vSwitch actually does have in-band control, and we know how to make the physical switches have in-band control. I mean, what basically would happen is one physical switch hooks up to the, basically you would have these 2 switches have direct connections to the controller. These would boot, get configuration, and then you could translate boot everything else. We just, frankly, it hasn't been that much of a customer push.
Okay.
And so we know how to solve it. It's not a non-issue, it's just not a big non-issue. It's not a big issue.
It's another business decision.
Yeah.
Okay. Cool.
But it is an important point that the expectation here is that there's a physically segregated out-of-band management network implemented in a switch or 2. I'm going to keep the camera guys entertained. So imagine you've just set up 16 racks of this. Imagine you've just deployed OpenStack or what have you. You now have a completely fungible collection of physical machines and virtual machines. That's fun. What do you do next? So we actually have 3 interesting management techniques, configuration techniques to actually chop this up. So the first we call a logical segment. The idea is it's a lot like a VLAN or a VXLAN or something like that. It's an L2 broadcast domain. You're saying, and the configuration actually looks exactly like this. You say, this switch, this port, this switch, this port, this switch, this port, this switch, this port, and this random VLAN tag, all of these go into the same logical segment. And so translating this to how people do networking now, you can think of this as us automatically doing the equivalent of VLAN translation and VLAN trunking for you. You give us the inputs, we will program the rest of the network. Does that make sense? And so you can have different VLANs going into what's effectively the same L2 segment. This is really a translation layer. Of course, you can have multiple of these. And then where things get interesting is you can connect these together using what we're going to call a logical router. Now, a whole lot of questions on how we implement the logical router. That's actually the cool part. But the concept is, this is for all intents and purposes a physical router. We allocate an IP address here, an IP address here. You can ping those IP addresses. You can trace route through them. And it's really a policy hook to say, when you go from this logical segment to this logical segment, here are the sets of L3 routes, the sets of ACLs, the sets of service chaining policies. This is like a unique policy container for all the stuff associated with this tenant. And the back end of this is actually implemented much like on the hardware, much like you'd implement a VRF. So there's actually, think of this as a simple way of exposing VRFs to folks. And of course, you can have multiple of these. And they are completely isolated, assuming that's what you want. And then there's this thing that we call the system router, or the times you want to configure a policy to actually connect them. And this will become clear when I actually show you the graphical user interface, because I actually think the user interface is even clearer than the slides. Does the concept at least make sense before I talk about how it's implemented?
System routers distributed across all nodes in terms of reachability and whatnot.
The implementation of this is the tenant routers. This is where I mentioned before that we have distributed routing in hardware. The tenant router is basically every leaf gets its own copy of the routing table of the ACLs and things like that. And every leaf will reply to all of the gateway IP addresses for the logical routers that it's configured for. So basically what happens, if you imagine you've got, so if this physical machine is talking to this VM in this rack, he goes through, that's a strictly local operation. If this guy is talking to somebody else in a different logical segment but in that same rack, he's only going local to his rack, even though they're going through that same logical router. The idea is that, so this may sound funky, but it's actually, the properties are really nice. It means that there's never hairpin turning. Every route has multiple paths, and all paths are active-active. And whether things are L2 hops or L3 hops from each other is strictly a matter of policy and can happen kind of arbitrarily through the fabric.
Are those flow mods also pushed down to the virtual layer, so you could do the interverf?
And now that we have control of the virtual switch, we actually push that down to the vSwitch as well.
Cool, so no Tor hairpinning or anything like that?
Yes.
All right, cool.
So you mentioned logical is local, but system level.
So you can think of it as the logical routers are implemented on the leaves, and the system routers are implemented on the spines.
Got it. Okay.
So if you're actually going to go hop, 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 it will actually bounce through the spine layer, but that's what chassis routers do. Like quite often, if you're routing through a chassis router, if you're going in and out the same line card, quite often you'll still bounce through the fabric anyways. There's really no appreciable performance penalty for this.
So a leaf switch, just to make sure I've cleared my mind, a leaf switch may have multiple virtual routers. A logical router, rather. A logical.
I mix it up too.
Yeah, a logical router that is routing for the same segment, say the green segment up here, that can exist on multiple leaf switches.
Yeah.
But they don't communicate. They're not. It's not like a distributed virtual switch. It's not a distributed virtual router.
So think of it as the data plane is distributed. The control plane, that is the thing that decides what the policies are and how to distribute them, that's managed through the controller. So there's no control plane protocol running between the logical routers.
But you do have
No, actually, so it just occurred to me as I said that. So as we're adding, we've got BGP support coming down the line. You could actually, in theory, set up BGP sessions between them, but don't do that. Like, it's just a bad idea.
But to answer that question maybe a little differently too is here you have one logical router green, one is orange. If you just look at the green one, you can add another logical interface to that, call it purple. To go from green to purple in any rack, you're not going to leave that leaf switch. Is that accurate? Or
so the expectation is that all inter-tenant communication goes through the system router.
No, I'm saying single logical router with
yes.
two interfaces,
yes.
And you hypothetically have VMs or hosts,
and you'd be completely local. Yeah.
Okay.
And to be completely. So think of this as, and I think this is actually really the hard part about understanding virtual networking. You've got the physical topology, and you've got the logical topology, and both of these are simple in and of itself. It's the mapping back and forth that gets complicated for us mere mortals. And that's the thing that we try to do, that we try to provide. We provide the mapping, we provide the tools to understand the mapping, and I'll talk about our test path thing in a bit that actually shows you, given 2 points, what's the mapping through the physical network and what's the mapping through the logical network. And it's the ability to have a computer solve the mapping between the physical and the virtual network for you that is one of the main value props of our product.
I guess I might not have asked this correctly the last time. In terms of inter-VRF traffic going between, from orange to teal, if you have two virtual machines,
You're better with colors than I am.
Thank you. If you have two virtual machines in those networks, and they need to communicate, that still has to go to the spine because that's what the system router does. Okay, cool. Thank you. Have you measured any? I imagine from a performance perspective, like joins and removes, you have to make certain flow modifications when a new logical network is created. You don't have to pass anything. I'm curious how you've hierarchically divided that. So if you have a new VM, for instance, join, only the logical router needs to make any modifications to its tables. The system router does not necessarily.
Yes, exactly.
Okay, cool.
And so we actually have a patented, literally patented algorithm for basically calculating the diffs out of what the low-level memory changes need to be and only pushing the diffs.
Oh, cool. That's pretty cool.
So we've got some pretty advanced stuff there. So think of this as a nice way of chopping up the network. And by the way, I will spend a whole bunch of time going through the demo of how this looks in practice. I talked about the zero-touch fabric stuff. Basically, you turn on switches, it downloads the operating system, it downloads its configuration. It also automatically discovers all of the links in the network, so you don't have to manually set up lags, you don't have to manually set up ECMP inside the fabric. We also have some host discovery protocols using LODP and LACP, so that depending on what's running here, you actually maybe don't even have to set up these lags. So think of all of the intra-fabric stuff gets set up for you, both at the L2 and L3 level. If you've got miswired cables, we'll tell you about it. And we do our best to set this up, although it depends on what you're running here. And if you're running our vSwitch there, then that's also gets set up automatically. The Hitless Upgrade details, these are actually the commands to do the upgrade. Basically, you copy the image from wherever you have it. You run the stage command, which actually does the copying to everywhere. And then you run the upgrade launch. And just briefly, if this server is dual homed, if it loses this one, it fails over. If this comes back and this gets lost, it fails over. So we can actually do the upgrade as using that functionality, where we upgrade this one, it comes back, we upgrade this one, it comes back. And because the controller has a global view, it can decide the maximum set of nodes to upgrade all at the same time without losing connectivity. And it has a whole bunch of sanity checks in it in terms of, is enough of your fabric working right now to even make a hitless upgrade viable? And that's actually kind of the hard part in a lot of ways.
But presumably you have to tell the system that those two switches are in the same rack, I guess.
Yes. And I probably won't cover this. I'll hit it briefly. Basically, you say, this switch as identified by its management MAC address is a leaf. This switch as identified by its management MAC address is a leaf. And these two are in the same rack. Yeah. That's the configuration.
Presumably, sorry, go ahead.
Sorry.
Typically in leads, you don't have them connected. Why you have those connected on yours?
So this is another literally patented thing. By having this link here, we actually can do link repair operations faster. So imagine the case where this link goes down. So this switch is up. Normally what would happen if this link was down, if you had a distributed protocol, you would have to actually withdraw the route from here and affect everything else and effectively end up disabling this leaf, and that's bad. By having this link, this is only used in backups as a backup link. What it changes this to from a complex distributed repair operation to a local repair operation. So he can continue to accept packets destined for the host he doesn't have a path to, shunt it over this way, and have them still come over.
You do it in pairs, you don't connect all of them together.
Only in pairs, local to a rack.
So in short, that's not required for doing MLAG.
It is not required for doing MLAG. It is part of the recommended deployment policy.
Sure, it's just not like your
that's not the control channel for our MLAG, which other people do use that for.
Yeah.
So in a fully scaled out 16 rack topology, how long does that take?
The upgrade?
Yeah.
It's under 15 minutes.
Under 15 minutes.
That was the number we got from engineering, but I thought all of our internal numbers were more like 10.
Yeah.
It doesn't matter. Under 15.
38 switches, 32 leaves, 6 spines, and 2 controllers. Together, the entire fabric is under 15 minutes.
And it's really like 2 passes, right? So you think of it as you do all of the lefts and like half of your spines and the standby controller. So that's all going in parallel. And then all that comes back up, the controller verifies that all that happened, and then you do the other half. And so it's really the time to update 2 switches because we can do all of it in parallel.
So is that link between the 2 leaves, would it carry any intra-VLAN traffic?
Say again?
Would that link carry any intra-VLAN traffic?
This link?
Yeah.
Potentially. So it's basically any traffic that would go on here, it will go on here if this link is down.
Again, it's only a backup scenario. It's
only a
just
backup
there
scenario.
for convergence.
Yeah.
It's not, nothing ever gets learned.
In the standard use case, that link is not used.
Right.
This is one of the coolest things we've done. People don't trust startups, it turns out. So we have to do kind of like above and beyond things to convince themselves that our products are useful. You guys heard of Netflix's Chaos Monkey testing? It's basically you do horrible things to your network to make sure your network can survive horrible things. We took the Hadoop TerraSort benchmark, ran it on a big scale-out cluster, ran it in about 7 minutes, and then we ran it again a whole bunch of times doing horrible things to the network. We killed the active controller every 30 seconds, a random switch every 8 seconds, and a random link every 4 seconds. Keep running the benchmark, and the net result is there wasn't an appreciable change to the benchmark rate. Which, translate that to the real world, it is, if bad things happen to your network, much worse than they should happen in real life, your applications keep going without really noticing. And one of the white papers you guys have in front of you is the details of this.
Unidirectional links.
We discover them. I don't think we will actually utilize a unidirectional link. We will flag it. You're thinking
you can
like
detect it.
We can detect it.
Well, I just read a paper that was all sorts of horrible things that happen in networks, which aren't always clean.
Yeah.
It's their partial failures or just weird crap. And
so
that was
our
one of them that
topology
stuck in my
discovery
mind.
algorithm is unidirectional. And so if you get the rawest low-level dump of our link discovery protocol, which you can from the controller, you see all the links it discovers are unidirectional.
And so you'll discover the unidirectional link.
Yeah. And we will
again,
flag it.
So there's a constant discovery process that's going on.
Yeah.
You initially discover and then
Yeah.
maintain, and when links go down and a unidirectional link shows
Well,
up.
and what's nice, even in the unidirectional case, you still get the link down on one side, which is it's easiest for us to detect and react to. Stuff that is cool that I won't get a chance to talk about. Actually, I'll show this in the demo. We've got this amazing Fabric Analytics stuff that takes all of the stats, the config changes, the network events, syslog, dumps them into Elasticsearch. Are you guys familiar with Elasticsearch? It's basically this like nice fungible open source tool that you can get. This is all stuff that you guys would normally spend your lives trying to build around somebody else's networking product. You don't have to use ours, but I think it's kind of nice. It just works out of the box. It just works into the larger philosophy. And I mentioned that you can actually program all of the config through REST API if you want. Brand new feature announced today. You can actually span from any 2 ports in the Fabric from one port to any other port in the fabric, whether it's physical or virtual. We call this the fabric span feature. So imagine you get a trouble ticket that VM X is misbehaving. With a very simple command, you can spin up another VM and dump traffic from VM X to your VM and figure out what's going on. Or maybe you don't want to dump it to a VM. Maybe you've got a network packet sniffer that's only one place in the network. This happy animation is actually showing, you can consolidate all of your network packet sniffers and dynamically pull things from different places without having to go down to the data center and wire it yourself, or get in a plane to go to the data center, depending on what type of data centers you work in. I mentioned that brand new, announced yesterday, we also control the virtual switch. This is our Switchlight V switch edition. The main benefit I shouldn't say the main benefit, one of the huge benefits of this is we actually solve the OpenStack neutron scaling problem by having a distributed logical router, both in the virtual switch as well as the physical switches. How many of you play with OpenStack?
A little bit.
How many of you had problems with the stock L3 routing agent? This is a big thing for people. We also implement NAT and PAT on our virtual switch. So if you have floating IPs or things like that, if you want to do the security groups, those all get implemented there.
Is this only for OpenStack? Is this only P plus V, or can you do just V?
You can do just P. You can't do just V.
Okay.
So I have a few questions from a vSwitch perspective. First off, I read a little bit of the Switchlight. You call it VX, I believe, right? So that's from what I can tell, it is a user space agent on top of OVS. Awesome. Okay, I'll let you elaborate and then I'll come back.
Sorry, someone told me once that the talk is going well when the answer to the next question is the next slide. I hope that's true. Tell me. So on the left, this is kind of an approximated view of what stock OVS looks like. Mm-hmm. So you've got the OVS OpenFlow agent, connects to a stock OpenFlow controller. There's this OVS vSwitchD, and built into that is a knowledge of the OpenFlow protocol. Mm-hmm. And critically on the bottom, it actually talks to a packet switching kernel module, part of OVS. We actually reuse that packet switching kernel module. Not that we couldn't develop our own, but actually this is in the kernel code. Like if you go to kernel.org, you get this. And for some of our customers, that's actually really important. They, for reasonable reasons, don't want weird random code they don't know running in their kernels. But we replace everything else out of this. We put our Indigo OpenFlow agent on top. We've got our own driver that talks to this. And critically, we've got effectively the custom Big Cloud Fabric pipeline, the same pipeline that the switch sees, the physical switch sees, built into this with some extensions.
Have you implemented or used OVSDB server, or do you have no need for that?
We have not used OVSDB server. All of our control protocol is actually, I shouldn't say all, almost all of our control protocol is built into the OpenFlow channel. We've done extensions on top of that, so we haven't had the need for that.
So you have from a Neutron plugin perspective, you're not using any stock plugins. You have your own, I presume.
We have our own.
And that's not ML2, that's full blown?
So as of yesterday, it is now full blown.
Okay.
The version that we were shipping before that was ML2. And critically, it actually doesn't talk to the switch at all. It talks to the controller, which transitively talks to the switch.
Yeah, okay. I guess the only question that I have is, have you done any testing from an I/O perspective? And this is, I guess, a little more important when you talk about containers. Performance-wise, because you say on your white paper, I think you did this for performance reasons, among others. Have you done any testing with respect to flow mods with instantiation of just hundreds of containers a second, things like that? Past that, those performance numbers up the layer from virtual to Tor to Spine. Have you done any testing there?
So yes, I don't want to quote numbers off the top of my head. Can I get you them after the
Absolutely,
talk?
Yeah, that'd be great. It's just interesting, just because that's like the one metric that's exponentially increasing these days, other than bandwidth.
But at the end, we're hundreds per second is not a big number for us.
Sure.